Hello, everyone. My name is Robyn Brooks, and today I'm going to be introducing you guys to three types of topological complexes: simplicial and cubical and CW complexes. So as a topological data analyst, I use these types of complexes every day, and I'll explain to you how I use them briefly at the end. So let's get started. First, we'll talk about simplicial complexes. We build simplicial complexes out of simplices. So a K-simplex is the smallest possible polytope of dimension K. Here are a few examples of simplices of dimension 0 through 3. These are all the ones that I'm able to draw. So the 0 simplex we call a vertex. The 1 simplex is an edge. 2 is a triangle, 3 is a tetrahedron, and on and on and on. We can have simplices of any dimension that you want. And you can see that the higher dimensional simplices have boundaries that are composed of lower dimensional simplices, i.e. the 2 simplex is bounded by 3 edges and 3 vertices. This is a general pattern, and we call these bounding simplices faces. So that's great. We can describe simplices in Euclidean space by giving a purely geometric description of the simplex. Here is set notation for the standard K-simplex. It's just the convex hull of the K+1 standard vectors in Rn. So like I said, we use these simplices as building blocks to build simplicial complexes. And we define a simplicial complex to be a finite collection of simplices satisfying two properties. First, if we have a simplex in the complex K, then all of its faces also have to be in K. Second, we require that the non-empty intersection of any two simplices be a face of both of those simplices. So here is an example of a spooky simplicial complex. You can see that property 2 here amounts to us building the simplicial complex by gluing simplices together along faces. Some non-examples of simplicial complexes include shapes or polytopes that are not simplices themselves, shapes that might be missing one or more faces, or complexes where the simplices don't intersect along faces. Finally, we can also define an abstract simplicial complex, which doesn't have to be a polytope in Rn. An abstract simplicial complex is defined as a collection of subsets of a set S with the property that if X is a set in the simplicial complex K, then every non-empty subset of X is also in K. This is tantamount to saying that if X is a simplex in K, then all its faces represented by these subsets are in K. Okay, cool. So next, let's talk about Euclidean cubical complexes. To build these, we need to define cubes in Rd. We give Rd the product order. Then for any two comparable points P and Q in Rd, we define the cube from P to Q as the closed interval between P and Q under the product order. The dimension of the cube is the number of non-zero entries in the vector Q minus P. And if P and Q have integer coordinates and differ by either 0 or 1 in each coordinate, then PQ is called an elementary cube. Just like simplicial complexes, cubes have cubical faces. If tau and sigma are elementary cubes, where tau is contained in Q, then tau is called a face of sigma, and sigma is a coface of tau. So let's look at some examples. Here's the 0 through 3 dimensional cubes, right? My 1 cube and my 2 cube and my 3 cube, etc. So now we can define a Euclidean cubical complex, and this is just going to be a subset of Rd that can be written as the union of elementary cubes. So here's an example of a Euclidean cubical complex. And again, just like simplicial complex, if a cube is in the complex, so are all its faces, and the cubes that intersect each other along faces, cubes have to intersect each other along faces like a simplicial complex. Some non-examples, well, a standard simplex is not a Euclidean cubical complex, and other subsets that cannot be written as the union of elementary cubes are not going to be Euclidean cubical complexes. More generally, sometimes we think that things have a Euclidean cubical complex representation, so we can write them semi-abstractly and then have a geometric realization as a Euclidean cubical complex. And when we have objects like these, We require that we're not allowed to self-identify faces, meaning we can't glue faces of the same cube together. Okay, last but not least, we have CW complexes. The definition of a CW complex is constructive. So we build a CW complex in the following way. We start with a discrete set, x0, and we call these the vertices of x. Okay. Inductively, we form the xn skeleton of x by attaching n cells, open balls of dimension n, to the n-1 skeleton via attaching maps. So, for example, a one cell is an open interval and its boundary is S0, the zero-dimensional sphere. So we therefore are going to attach one cells to the zero skeleton by identifying which vertices will bound each one cell, and we get a one skeleton, right? We're going to iterate, so we do this again. We take two cells, these open disks, whose boundaries are just circles, and we attach them to the one skeleton using attaching maps. So we can go on and on forever and just keep adding open balls of dimension n, increasing n, or we can stop at some dimension n. And our our CW complex is going to be the union of all its skeletons. We topologize our CW complex using the weak topology, so that a set U is open in X if and only if its intersection with the K skeleton is open for all K. So the reason we call this a CW complex is that it stands for closure finite weak topology. We've already seen that, we topologize this with the weak topology. We also call it closure finite because it is a closure finite space. This means that for each n cell, the image of the boundary of this cell is covered by finitely many cells of dimension less than n. So let's look at some examples. Both simplicial complexes and cubical complexes are CW complexes, but there are also many more. Non-examples for CW complexes are going to be spaces where we have an n cell that wasn't glued to the n-1 skeleton, or if we create something that's not closure finite. So for example, if we had a disk with infinitely many zero cells as its boundary, that wouldn't be closure finite. Okay, lastly, I told you at the beginning of the video, I would tell you how I use simplicial complexes in my work as a topological data analyst. Well, oftentimes, in TDA, we use persistent homology, where one defines a complex on data with the goal of identifying topological features of the data. So this complex is created using the data and associated parameter representing a relationship between data points. And we allow this parameter to vary, obtaining a filtration of complexes from which a persistence module is created. So a filtration is just going to be a function from some sort of poset to a complex K with two nice properties. For each P in the poset, we call this poset often parameter space. F of P is a subcomplex of K. And for each pair of comparable parameter values, P and Q, if P is less than Q, then F of P is a subcomplex of F of Q. Okay. So here is an example of a filtration of a simplicial complex. And you can see that at each step of the filtration, we have an associated inclusion map. And there are tons of different types of filtrations that are useful for persistent homology. You should go check them out. Thank you for your time.